All right. So a little bit of administrative work here. Test number 2. Test number 2 is scheduled for April 2nd. Now, I never move tests until, unless I have made a mistake, and that's today. So kind of an oversight. It feels like an oversight. I like to have tests before a break so that you can actually have a break from me and stats. And so I want to move our test to the Thursday before Easter instead of the Tuesday immediately after Easter. And so obviously a little bit less material. So yay for you. Right, and so kind of an oversight. I think I just missed that it was Easter when I was laying out my schedule. There's another reason, is because I want to stay with the other sections and have kind of similar test dates. And so I am moving it to Thursday, March 28th. Oh, that's for later. Okay, so it's just the Thursday before Easter instead of the Tuesday immediately after Easter. That's all. Okay, now if that's a problem, if for whatever reason, then you have to let me know ASAP. But this is what we're doing. Okay.
Oh, yeah, I do that.
All right. Any questions about that before we? So a little bit less material because we'll have one less day of stuff to cover. So that's nice, I guess. But all right. And then you can have a proper Easter break. It's just short, but still. At that point, we need a break. All right. So last day, we introduced hypothesis testing. So just a little bit of review. Hypothesis testing. And I gave you a problem to work on. Before we start that problem, well, I guess that's the end of the review, only because I'm going to reiterate everything that we said as we solve the problem. And so I don't want to write it out twice, but what we skipped last day was talking about the conditions. So the conditions that need to be satisfied for doing a hypothesis test. So I want to introduce those here. If you've run out of memory space, that's totally fine. Is that on my Zoom? I don't know. So that's totally fine. On the test, it's going to be little check boxes. So as long as you remember which boxes to check, right, what the conditions that you should be checking are, then you're fine. Okay. And so just briefly, I want to talk about the conditions for a hypothesis test for one sample proportions, which is the only type of question that we have introduced so far. Next week, we'll start comparing, well, what if I have two samples, each with proportions? What if I want to compare those to each other, right? And so maybe the proportion of voters in one state compared to another state, right? How they vote in favor of some candidate is a kind of a common example. And so the conditions for inference are these. So the first one is still independence. And maybe I shouldn't number them. I'm just labeling it the independence condition. You might remember from the confidence interval, right? we had two sections of conditions. So the independence condition and then the normality or the sample size condition. We're gonna have the same setup here. In fact, the independence conditions are all the same as the confidence interval. So that's an easy win, right? And then the normality one is just, it's very similar with a twist. So the first one, let's remind ourselves what the independence condition was. It was randomly sampled observations, right? We had to collect a random sample, and then we can assume that those observations are independent of each other. That's nice. The second condition, which I'm going to call optional, and I won't include it on the list of conditions to check off, so you don't have to worry about it. But I'm a slave to completeness, and so the n less than 10% of the population is a condition. If you've sampled too much of the population, you're introducing non-independent observations. So that can be a problem, but it never really is a problem. So that's why I make it optional. So if you forget all other conditions, just check off the randomly sampled. That's always going to be a condition. So you can always check that off and then forget about all the rest. That's good for part marks. All right. So now the normality condition, and I'll make a note here that this is the same as for a confidence interval. The normality condition, or we could call it the sample size condition, is kind of, it's different for hypothesis testing, although they're going to feel very, very similar. Let's think about what it was for a confidence interval. For a confidence interval, we had to have at least 10 observed successes and at least 10 observed failures in our sample. Now, in hypothesis testing, we have some hypothesized proportion or an expected proportion. So now we're going to talk about, we have to have at least 10 hypothesized or expected successes. I'll write expected / hypothesized successes. How you're going to calculate that is you're going to take n, so your sample size, times p naught, right? Where p naught is from your null hypothesis. And so you're going to do n times p naught, where p naught is from your null hypothesis that p is equal to p naught. Remember, p naught is the value that you want to compare your sample proportion to. Okay, so n times p naught has to be greater than or equal to 10. And I'll say in the confidence interval, right, we had at least observed, which is n times p hat greater than or equal to 10. That's the only difference, nothing crazy, right? But we have to have at least 10 successes and 10 failures in general. Sometimes they're expected and sometimes they're observed. But in the similar way, we have to have at least 10 expected or hypothesized failures. Expected or hypothesized failures. How you're going to calculate that is n times q naught has to be greater than or equal to 10. And just as a reminder, where q naught is 1 minus p naught, of course. Right? The q is always 1 minus the p. Right? Versus in a confidence interval, we had the observed, which was n times q hat, had to be greater than or equal to 10, right? The observed failures. So just minor differences. Like I said, not really worth the brain space. I wouldn't be doing my job if I didn't outline the differences and there's all these ins and outs. But ultimately, as long as you have 10 successes and 10 failures, you're good to go, right? So that's kind of the broad strokes. Good to go, she says. What does that mean? You're good to go on your analysis. Now we can actually do the hypothesis test, or in the confidence interval, we can actually build our confidence interval. So let's see here. So now that we have these conditions up our sleeve, I want to go ahead and do this example. What I found with this example, and I'll copy and paste it here, is that it introduces a special case right away, which I don't love because it's kind of confusing. And so let's just have a read. And I'm assuming that you tried it. And if you have, you might have gotten stuck on the p-value, right? Because we haven't really seen a concrete example of how to solve it. In fact, today I want to show you 2 different ways that you can find the p-value, and you should be comfortable with either way. All right, so we talked about this survey last day where they asked 850 respondents about how they feel about different things on Facebook. Oh, maybe I haven't muted everyone. Is that what's going on? I keep hearing things, but maybe that's just me. Let's see here. Okay, sharing my screen. So now we have the same 850 respondents, and they're asked how comfortable they are with Facebook creating a list of categories for them. And 41% of the respondents, and so immediately I'm going to make a note that if it's of the respondents, that's sample information, right? So that makes this a sample proportion. And so here, of the respondents, says that this makes p hat equal to 0.41. Right, p hat is a sample proportion, and so that's my sample proportion. 41% is a little bit too far from where I want to be, and so later we'll also consider. We will also consider an example where p hat is 0.46. That's tiny. I'll introduce it, but okay, just to see the different scenarios. And so, but for now, we can start with 0.41. Okay, and so 41% of the respondents said that they are comfortable. Do these data provide convincing evidence that the proportion of American Facebook users, and I'll just insert here, who are comfortable with Facebook creating a list of interest categories for them is different from 50%. Okay, I have a sample proportion 0.41, and I want to compare it to 50, which is 0.5, right? And so that tells me that P naught, remember P naught is the number I want to compare my sample proportion to, is 0.50. That's really difficult when you're first starting out reading a question and figuring out what your P naught is. Right, and so just remember that you have your sample proportion. That's not it, right? You know what your sample looks like. You have everything that you could possibly want to know about your sample. That's not what we're hypothesizing about. We're hypothesizing about how it relates to 0.5, right? And so that's what makes your P naught 0.5. We're also told that we want to know if it's different than 50%, which is going to translate to not equal to 50%, right? We could say, is it less than 50%? That's the other option. But just to cover all our bases, we're going to consider it being different than 50%. What I want to highlight here is whenever it asks for evidence, then that's going to be asking for a hypothesis test. You have to do a full hypothesis test. Okay. So is there evidence that blah, 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 right? Then you have to do a full hypothesis test. Okay. So let's see here. Let's start with step 1. That's a good place to start. Step 1 was what? State your hypotheses. State the hypotheses. From the formula sheet, where is it? We've determined, or kind of imagine that you've determined that you have a one sample proportion type of question. That's your first goal, right? In fact, on test 2, what I'm going to do is I'm going to make you do confidence intervals and hypothesis testing properly. And then I'm going to give you a series of question blurbs. And you have to tell me what type of question it is and what the null and alternative hypotheses would be. But that's it, right? For each of those blurbs. So you have to be able to read a question, tell me what type it is, what would your null and alternative hypotheses be, and then move on. So it's kind of like a, did you guys do mad minutes in school? Kind of, I think they probably got rid of them because they're so stressful. You do like 100 math problems in a minute. It's a mad minute. And so it's a mad minute of hypothesis testing. And what's so incredible is we used to do it, no problem. Right? Addition, subtraction, multiplication, division. Now I'm terrible at mental math, but I guess I could do a mad minute at some point. I know I could. All right, so we've decided that we have a one sample proportion type of question. That's our first step. Now we're limited to that area on our formula sheet. That's the only area that we've seen so far for hypothesis testing. And so then we're going to narrow it down to a hypothesis test for P. And it tells me what my null hypothesis should look like. And it also tells me how to calculate the test statistic, which is a Z in this case. And so to state our hypotheses, we're going to follow the same format here. P is equal to P naught, but P naught is just a placeholder for a number, okay? In fact, we're going to use 0.5. Right? And so that's goes here. The value I want to compare my sample proportion to. Now, in order to show that 41% is significantly different from 50%, I first have to assume that it is 50% until I have proof otherwise. And so then the alternative hypothesis is usually what I want to show. And so I still have to talk about P and how it relates to 0.50. But the equality is already taken up in the null hypothesis. That's great. And so here, from the question, how do I? Right. I want to know if it's different than 0.5. So then I use a not equal to. Right. Here, I personally like to make a note to myself that this is a two-sided test. right? Because I have a not equal to, so I don't care which extreme. In fact, I'm concerned about both extremes of the tails, right? And so here, I'm gonna make a note to myself that this is a two-sided test. You don't have to do this, but it's one of those things where people find it very, very confusing because we don't need that until step 3, which is going to be in a while, right? There's a lot of stuff that happens between now and step 3, and so then it's nice to have a little reminder that, okay, this is a two-sided test, which means what? I need to find the area in both the tails, right? Instead of just the one. Okay? Now, but really, all you need in step 1 to state your hypotheses is this dark blue section, right? Everything else is gravy. All right. So now this is where I'm going to sneak in our conditions, right? And so I'm going to sneak them in here. Check the conditions, which I hadn't introduced last day. So if you worked through the problem and you didn't check the conditions, well, you didn't know what they were yet, so that's fine. The independence condition, oops. The argument we used, and I'm just gonna remember what the question was from way, I guess it was just last day. It said, a representative sample. So how we're going to phrase that is we assume that it was randomly sampled, right? We assume, and that's the same blurb that we used last day for the confidence interval, or I guess the day before last. We assume the sample was randomly sampled. That's good. And this one's optional. N equal to 850 is less than 10% of the population of American Facebook users. Less than 10% of the population of American, oops, Facebook users. The normality one is the new one. That's the one I'm rushing to. The normality condition. The first one was I have to have at least 10 expected successes. So N times P naught, right, or hypothesized successes. 850 is my N. And P naught, well, from my null hypothesis is 0.5. So I would expect half of those 850 to be successes. So 425, which is greater than or equal to 10. So that checks out. Then, and so it can be as simple as that, right? Just remembering that this is the expected successes or the hypothesized successes. And then we can do the same thing. 850 times 0.50, which is also 425, which is also still greater than or equal to 10. Therefore, the assumptions or the conditions for the central limit theorem are satisfied, right? Which means we can go ahead and do this hypothesis test. So therefore, the conditions for the CLT, the central limit theorem, are satisfied, period. I didn't say it as if it was a period. That was weird. And I managed to get lines on my paper finally. Had to dig deep. All right. Now we're ready for step 2. Step 2, wasn't that a whole page long? Yes, it was, I know, but these are long. Step 2, I call it do the test. Technically, it's calculate the test statistic, but that sounds boring, so I call it do the test, do the do. Doing the test means do the calculation that's given in the formula sheet, right? So in the formula sheet here, this is step 1, this is step 2. In our case, we're going to calculate Z, and Z is going to be this. Z is P hat minus P naught, right? How far is my sample proportion from my hypothesized proportion in terms of the spread of the hypothesized proportion? So it changes just slightly, P naught Q naught over N, and then square rooted, right? But in terms of the standard error of the hypothesized population, right, how far is my P hat from P naught? Okay, now finally we have numbers that we can plug and chug here, right? Remembering that P hat is 0.41 and P naught is 0.5 and N is 850, we're ready to go here. So Z is going to be 0.41 minus 0.50 divided by the square root of 0.50 times, well, I'm not going to write 1 minus 0.50 because it's 0.50 divided by 850. Now, you know what? It's gonna take so many lines. 0.5 times 0.5 divided by 850, and then take the square root, and then I'll jot down the number. But first I'll do 0.41 minus 0.5, oops, 0.5. Negative 0.09 divided by, and 0.5 times 0.5 divided by 850, and then taking the square root, I have a standard error, so a spread of 0.017858851. That's my spread. So I've gone a distance of 0.09 below the hypothesized proportion, and in increments of 0.017, that's really far, right? And so now we get a Z of negative 5 point, now what was it? 247856705. All right. That's really far into the tail, right? In fact, any Z that's beyond 2 standard errors away means that we're most likely going to reject H naught. Okay, so just as having kind of a check-in point, okay, this tells me I'm going to reject H naught, because we understand, whoa, that's really unlikely to happen, but we need to be able to communicate it in terms of probabilities. Okay, and so, and I'll just jot down, whoops. So Z is my test statistic, and I get negative 5 point whatever. All right. Now, step 3 is finding the p-value. That is that probability that we're after. So step 3, find the p-value. I want to do kind of an aside here because I want to show you 2 different ways of finding this p-value. The first one is the Z table, which is going to be very similar to using software, Excel, or whatever you want, right? And then I'm going to show you how to use the t-table to find just kind of a rough approximation, which is what I'm going to stick with later on. But you're expected to be able to use both because you're so comfortable with the z-table already. Ah, we are? All right, you are. It might be helpful to just kind of visualize what's going on here. Z is centered on 0. And I have some Z way out here at negative 5.248. Okay. So I know that my one-sided p-value would be the area in the tail here, right? It's this area in the tail. That's my p-value, my one-sided p-value. Okay. What do we also know? We've seen this before in the z-table. I go to use my z-table and what happens? Well, okay. Oh, need to erase this there. So from the z-table, I'll just snag the lower values. The smallest value of z that's on here is negative 3.49. That's okay. We know how to work with that, right? So what can we say? We can say, okay, here at, and maybe I'll use a different color. Orange. So now what the table is saying is that once you reach negative 3.49, the area in the tail is 0.0002. That's very, very, very small, right? It's essentially 0. How far would you have to go to get to an area of 0 though? You'd have to go to negative infinity, right? And so everything past negative 3.49, you're just going to say it's less than 0.0002. That's really small, right? But there was another problem. We had a two-sided p-value, and so I'm going to replicate this very tiny area in the upper tail as well. And so I'm going to have, right, 5.248. So this is what I mean by making a note in the very beginning in your hypotheses, whether you have a one-sided or a two-sided test, because that's going to tell you if you need to replicate the area in the tail or not. So since we have a two-sided test, right? HA says that P is not equal to 0.5, right? This is what makes it two-sided. Oh, and I guess, haha. Yeah. No, that gets weird. How do I do this? I can shrink this up. Haha, sneaky. Wow. Not very easy to read anymore, but we don't need it. So since we have a two-sided test, right, from the alternative hypothesis, and that's the disconnect that people really struggle with. And so we multiply our one-sided p-value by 2, right, to replicate it in the other tail. We multiply our one-sided p-value by 2 to replicate it in the other tail. In our case, we find that the one-sided p-value is less than 0.0002. you're allowed to say approximately 0, but you're not allowed to say 0, right? Because it's not negative infinity, right? You're never going to get there. So you can say approximately 0, that's totally fine. But let's just focus on less than 0.0002. So we found the one-sided p-value is less than 0.0002, which means our two-sided p-value is less than 2 times that, right? So the two-sided p-value is less than 0.0004. Multiplied by 2, it's still very small. You're allowed to say, or approximately 0. I would probably recommend just writing it out in words, right? Because the alternative that you have, so, or you can use notation. The two-sided p-value, that's still words, I guess, is 2 times the probability that z is less than or equal to negative 5.248, I think it was. Yeah. Which is less than 0.0004. You can say that, that's allowed, but there's a risk if you're not comfortable with that notation that you say something that's not true, right? And so it's always safe to just write it out in words. And so that's what I prefer. It's a little bit longer, but at least you can read through it and talk yourself into it or out of it, I guess. So, all right. So that's one way to find the p-value using the Z table, which we know and love, right? And so the other way that we could find the p-value that I'm going to be switching to is just using the T table. We can use the T table, and maybe I'll highlight here. Maybe I never said it. Okay, we can use the T table to approximate the p-value. Oops. So let's have a look at the T table, and I'm going to highlight that I'm talking about the T table now as opposed to the Z table, and you have to be comfortable with either or for the assignments, but on the test, you can choose which one you like, okay? Use whichever one you prefer, that's fine. I'll know what to do. And so then it's a choose your own adventure. What you're going to find, I'll bring up the T table first. So the Z table is 2 pages. Oh, it's so long. The T table is nice because it's only on 1 page. Okay. And we used it before when we had to build a confidence interval, because that's how we found our critical values, right? And so if I want to build a 95% confidence interval, what did we do? I said, okay, then my Z star must be 1.96. In fact, this Z star is just a Z. And so what I'm going to do is I'm going to copy that the last couple of rows from the T table. Now these Zs are just regular Zs. For some bizarre reason, it goes to 3 decimal places, whereas the Z table has 2 decimal places. And so that's why I've kept 3 decimal places earlier, whereas usually we would round it to 2. Just round to whatever matches your table. Okay. And so to use the t-table, we have to remember a couple of things, or kind of notice a couple of things. Well, first off, these are Z values, right? Z values as I'm moving further and further out into the tails. Okay. They're all positive, but that's okay, because what can I do? I can just drop the negative, and by symmetry, the area in the tail is the same, right? The area in the tail from positive 1.96 is 0.025, but also the area in the tail at negative 1.96 is 0.025. And, well, spoiler alert, the area in both the tails added up, or times 2, is 0.05. Really, we don't need this line. I just think it's nice to have, right? So then it eliminates some calculations, but you don't need it, right? Notice 0.25 times 2 is 0.5. It's just taking the area in the tails and multiplying it by 2 for your 2-sided p-value. So that's nice. All right, so we're leveraging that symmetry around 0 in order to just have 1 page instead of 2 pages, because it would look the same. So what would we do? We have a Z that we've calculated. Now what we're going to do is we're going to try to place it somewhere on this number line, right? It's going to fall between 2 values, okay? And and then we're going to be able to find a range for our p-values. Now, what I want to do here is just erase this for a little bit so I can copy this, because I want to make a note for completeness. So here's our, there. So our Z star is 0.674. But between the middle and 0.674, there's still area there, right? And the middle is at 0. And so what I want you to do is I want you to imagine having a 0 option. And let me just bump that. Right. So here we have this 0 option. Imagine your normal distribution at Z equals 0. How much area do you have in the upper tail? 0.5. So then the 1-sided P is 0.50. The 2-sided P, how much area do you have in the tail at 0? In both the tails, you have 1. So here, now on the flip side, right? And so what I'm imagining, oh, let's snag these 2, paste them in real small. There. What you're imagining, I know you are, is here at 0, right? Because Z is centered on 0. The area in the upper tail is 0.5, which means that the area in both the tails, right, 0.5 times 2 is 1. So that's what we're saying. Which means that somewhere between, let's say this one here, between 0 and 0.674, if you find a Z that's in that realm, right, that's not very far from your hypothesized value at all. So you're going to fail to reject the null hypothesis. But what that looks like here is you have 0.674, and it's saying that the area in the upper tail is 0.25. Now, if you pretend to have a negative 0.674 here, that also has an area in the tail of 0.25. So then the two-tailed p-value or the two-sided p-value is 0.25 plus 0.25, which is 0.5. Right? So now we take a trip down. I'm going to skip some of these because what can we do? Right, let's jump to 1.96. That's a go-to. So here at 1.960, we know that the area in the tail is 0.025. Makes sense, right? That's the critical value for a 95% confidence interval. So I either have 95% in this captured here, or I'm out in the tails by 5%, right? So there's that symmetry again. 0.025 at negative 1.960. Here, now, right, our Zs are increasing as we move out further into the tail. What happens to the area in the tail as you move out further and further? It gets smaller and smaller and smaller and smaller, right? In fact, at the very end here, the table stops at 3.29, but what happens? That's just, they gave up, right? And so here, at infinity, the area in the tail at infinity of one of the tails is 0, right? But only at infinity. And if I multiply 0 by 2, it's still 0. Yeah. So here at way out at infinity, let's say infinity is here, then the area in the tail is 0. But up until that point, we could even have maybe, let's jot this one down. 3.291 has an area in the tail of 0.0005. Very, very, very small. Multiply that by 2. It could happen on this end too. 3.291. So we're leveraging that symmetry and just using the positive values because they behave the same on the other side. Now, how do we do that? We're going to take the absolute value of Z. And so since the t-table only gives positive values of Z, we need to first take the absolute value of Z. First, take the absolute value of Z. And so the absolute value, in case it's been a while, you just drop the negative essentially, right? And so as an example, the absolute value of Z, an absolute value are just these vertical bars, right? And so the absolute value of Z equal to negative 5.248 is just 5.248. So it just makes it positive. So what we're going to do when we phrase this question is we're going to use the same, or I use the same layout always. Okay, and that's because I don't like thinking about inequalities. I don't like the less than, greater than, and so I just prefer to always have them laid out in the same way. Okay, and so that's what I want to establish now. We're going to say this. I like to start it off with like a, since the absolute value of Z, now notice how I'm placing it in the middle of the page. Why is that? Because we said we're going to take the Z that we calculated and try to place it on this number line. So it's going to fall between two values, right? In fact, I can put the less than here, Z equal to negative 5.248. The absolute value of that Z is between these two values. Okay, and I always put it in the middle of the page. This is always here, this is always here, this is always here. The Z value that we calculated changes depending on the question, right? But, oh, it looks all scribbled out, but, well, they're always there. So now I use the table to figure out which values bound 5.248. And so if I go, I can look at this image, which you won't have, but you could make, right? Or once you get used to working with the table, you can say, okay, I'm going to take my Z, I'm trying to place it 5.248. Well, 5.248 is somewhere between 3.291 and infinity, womp womp. And infinity. Right? So I'm just communicating what I did in the table. And so now, and again, starting in the middle of my page, because now I'm going to have bounds on my p-value. And I want to emphasize which p-value I have. Do you have a one-sided p-value or a two-sided p-value? We've established we're doing a two-sided test. So we have a two-sided p-value. So the two-sided p-value is also between these two things. So notice how I said, I don't like dealing with inequalities. I don't like thinking about them. So I just use the same ones in both lines, right? And you're always going to have the p-value, but whether it's one-sided or two-sided depends on the question. So I'm not going to highlight that. So now my two-sided p-value is between these two values. This is kind of the tricky part because we found our Z is somewhere in here. And we go to the two-sided line and I'm going to see that, okay, then my initial reaction is to list it as they appear, but that's wrong, right? Because the areas in the tail are decreasing as I move out. So I have to read these from right to left. Takes some practice getting used to, but once you see that, okay, well, 0 is actually less than 0.001, then it becomes kind of more intuitive. So my p-value, my two-sided p-value is somewhere between 0 and 0.001. In fact, right, this feels less precise than what we're used to, but it's enough. Is this range less than 0.05? Yes, it is. So we'll still be able to draw a conclusion based off of this range, right? In fact, recall from using the Z table, the two-sided p-value was less than 0.0004. Is that in that range? It sure is, right? In fact, if you wanted a more precise value, you'd have to use Excel or some other online calculator. Or if you've got your trusty TI-84 or 83 or whatever, it can do Z probabilities. So 10004 falls in this range. Either way, we come to the same conclusion, right? And so now it's time to state our conclusion. I'm going to need another page. I'll put it here. Step 4 is our conclusion. Yeah. Because I have the absolute values around, is this the one you mean? Yeah. Because I have the absolute values, I keep the negative from my calculation, but the absolute value drops it. Yeah. Nice. Okay. So my conclusion, now I'm going to state the conclusion using this interval that we found for our p-value, because that's how it's generally going to be set up. So since, right, what's the first thing I have to do? I have to compare my p-value to the alpha level. We weren't told what to use, and so what do we use? We use 0.05. So since the two-sided p-value is between 0 and 0.001 or less than, this part's optional because you only have to use one of the methods. But if you prefer the Z table still, you would say, since the two-sided p-value is less than 0.0005 or 4, either way, it is less than our assumed alpha level of 0.05. If it's not given, you can state your assumptions. It is less than our assumed alpha level of 0.05. Which means if it's less than our alpha level, right, we've moved far enough into the tails to say, probably reject H naught. And so now we have enough evidence. So therefore, we have enough evidence to reject H naught. If I'm rejecting it, I'm going to say in favor of what? In favor of HA. This is a lot of work, right? But we did it all to answer a question, so we should probably answer the question. And what I do is I take the question and I reword it as an answer, just like the confidence interval, right? I ask you to build a confidence interval, you have to interpret it. So same deal here. The question was, do these data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%? Well, we rejected H naught in favor of HA. And so we would say what? We would say these data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%, period. Just reword it as an answer. It doesn't have to be beautiful, right? There's fancier ways that we can say this, but it's not worth the trouble because we're just learning the steps of hypothesis testing. And so all I'm expecting you to do is reword the question as an answer, even if it's worded a little bit strangely. Okay, I'll throw a therefore in front. Therefore, these data provide blah, 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 blah. Okay. How am I doing for, okay. Now, I said, so that's the end of this question. I'll indicate that here. But I also said, how about just to see something more reasonable, right? We had a Z that's off the table and it's hard to think about, and it's relatively obvious that we're going to reject H naught. And so now I'm just going to grab this question again and what do I have to do to make my Z a little bit smaller, a little bit more on the table? I have to move my 41% closer to 0.5, right? Let's try 0.46. So I'm going to change this. Change to 46%. Step one is the same, right? So step one, same as before. So I'm not going to write that down because I want to focus on step two. Do the test. So now my p hat is 0.46 instead, something a little bit closer to 0.5. So now z is p hat minus p naught over the square root of p naught q naught over n. It is tempting to not write down the formula that you're using and just plug in the values, but in terms of retaining marks, when I'm marking, you're better off telling me, hey, I assume that this is the formula for Z. Now, if you copied it down wrong from the formula sheet and you follow through, I can give you almost full marks, right? It's wrong because you didn't copy it right. But as long as you follow through and tell me that you're doing what you said you were going to do, that's fine, right? How are you supposed to know mid-solution that you actually did it wrong? That doesn't make sense. And so I do follow through. It's more important that you do what you told me you were going to do, okay? And so it's definitely worthwhile to write down the formula before you plug things in. You don't have to, but it saves you marks. I know that for a fact. So now my p hat, I'm changing it just to 0.46. My standard error is the same as before, but of course I've lost it. So I'll write it down again. 0.50 times 0.50 divided by 850, and then take the square root of that. Let's see here. I think I get a Z of 8. Oh, not for me. Okay, and then I have 0.46. I'm just going to go for it. Minus 0.5 divided by that. I get negative 2.332380. Whoops. 758. This I know is on the table, right? That's nice. So in step 3, find the p-value. Now you have two options. You could use the Z table or you could use the T table. Am I going to be able to pull it off doing them side by side? I don't know. I haven't tried it before. It's going to be tight. Now, I want, well, maybe before I do that, we should draw what we want. The p-value, Z is still centered on 0. I have a Z of negative 2.332. The one-sided p-value would be this. I want a two-sided p-value, right? That's something to remember. Want a two-sided p-value. Okay. How can we find this area with the Z table? Let's focus there first. Okay, and then just remember that you want a two-sided p-value, which means you're going to multiply this area by 2. And that's your two-sided p-value. And so now I'm going to say using the Z table, the collective we, find the one-sided p-value is, now what's really nice in this scenario is that it is negative, and the table only gives us the area to the left. If we had a positive z, you'd have to do a little bit of 1 minus action, but not too bad, right? You know how to do that. Or what's the sneaky way of doing it? Just throw a negative on and then find the area in the lower tail from that, right? You've got options, but the one-sided p-value here is what? Let's see here. I want the negative side of z, negative 2.33. And I'm going to copy it in, and I'm going to make it really small, but once I print it to PDF, you'll be able to see it again. Okay. Is 0.0099. That's your one-sided p-value. Therefore, the two-sided p-value is 2 times that. Therefore, the two-sided p-value is 2 times 0.0099, which is 0.0198, I think. Let me just check. Yeah. Well, relatively exact, right? Software would get you more exact, but I think we're happy with that. Just looking ahead, this is less than 0.05. I'm going to reject my null hypothesis in favor of my alternative hypothesis, right? And so it's still far enough away from 0.5 to be considered significantly different, right? But let's do it with the t-table. We're going to find the same results, right? Just different ways and different levels of precision. So now, using the t-table, we have what? We find that since, and I'm going to use that layout that I introduced you to, and I'm going to keep using it all the time. And the reason I'm introducing it now is because we're still going to keep using it when we start calculating t's, right? And so the same method applies. So since the absolute value of z equal to negative 2.332, only because the t-table has 3 decimal places, so I'm going to keep 3 decimal places at least, is between 2 values. All right, let's grab the, wonder what's easier. Maybe I'll just snag a freshie. Here's the t-table. So here it is. I'm going to take the absolute value of 2.332, and I'm going to try to place, or I am going to place it, I will succeed, somewhere on this line, right, between 0 and infinity. And so 2.326 and 2.576, that looks like a good spot for 2.332. Right, somewhere between there. So now, depending on if I want a one-sided p-value or a two-sided p-value, right? I need a two-sided p-value, so I'm going to look at the second line and ignore the first one, unless you want to do some math. Is multiplying by 2 math? I'm not so sure. I guess technically. So 2.332, notice how I've placed it in the center here, is between those values we found, 2.326 and 2.576. So, and then again, starting in the center, the two-sided p-value is between two values. The two-sided p-value is between, from the table, 0.01 and 0.02. Being careful to read them right to left because they're decreasing as you move further out, right? That's the only thing that trips people up a lot is that switch. But just take a step back and make sure that you have a smaller value followed by a larger value. You could get weird and change your inequalities, but I find that that's more confusing, but you could do that if you want to. Let's check in. I have this range for my p-value. This entire range is less than 0.05. I would still reject H naught, right? So I can still use that range. And in fact, it'll never cross 0.05. It'll be either less than or greater than 0.05. From the Z table, we have a more precise value, 0.0198. 0.0198 is between 0.01 and 0.02. So that's nice. So now we have two ways of doing it, right? And even if you don't like this way right now, it is worth investing time and doing both ways, and eventually you'll like this way more, right? I guarantee it. So now, how am I doing? All right, enough time for a conclusion, I guess. Step 4, the conclusion. I need to stop wearing sweaters in this room. It's so hot. It's crazy. And I know, but I am wearing a shirt underneath here, obviously, but I'm really weird about taking a sweater off, like in class, feels weird. So I only did it once because I was about to faint. So, what's our conclusion? Again, I'm going to focus on my conclusion with the t-table, but I'll also throw in brackets using the z-table just so we can see that they're the same. So since the collective we, I guess, since our two-sided p-value is between, oops, 0.01 and 0.02, I think it was. And I'll throw from the Z table, or our two-sided p-value is 0.0198, depending on what method you choose. So since our two-sided p-value is between 0.01 and 0.02, it is less than our assumed alpha level of 0.05. Then our assumed alpha level of 0.05. Therefore, we have enough evidence to reject H naught, or maybe I'll say which means, because then I'll save my therefore for the end, which means we have enough evidence to reject H naught in favor of HA. And then I'm going to just steal this again. Therefore, These data provide convincing evidence that the proportion of American Facebook users who are comfortable with Facebook creating a list of interest categories for them is different than 50%. Okay, just a couple of notes before we close off here. I want you to be showing off. So these are all things that you've had to take into consideration as you solve the problem. So when it comes time for your conclusion, don't skimp on letting me know all the things that you know, right? So saying things like, you had to find a two-sided p-value and you know what it is, right? And you know what you're comparing it to, right? These are all things that you know, so you have to articulate them, right? Show off all the things that you know. And on that note, I'll leave you be, and I hope you have a great weekend, and I'll see you on Tuesday.
We done this.